Question number 3. A closed cylindrical tank filled with water has a hemispherical dome and is connected to an inverted piping system as shown in figure 3. The liquid in the top part of the piping system has a specific gravity of 0.8 and the remaining parts of the system are filled with water. If the pressure gauge reading at A is 60 kilopascal, so this is the pressure at point A, determine the pressure in pipe B and the pressure head in millimeters of mercury at the top of the dome, which is the point C here. So according to this diagram, we could say that we have a inverted U-tube. So this U-tube is filled with a special liquid with a specific gravity of 0.8. So we need to calculate what is the pressure at point B here. So and then we could draw a Pascal paradox line at this level. So and then we could calculate the pressure by creating equation of this point and this point. So from this line, we could write that point number 2 here is equal to point number 3, and this pressure is also equal to point number 4 here, which is equal to 60 kilopascal as mentioned in this picture. So and then we could start our calculation of pressure at point B here. Okay. The point B here will feel the pressure because it has 2 meters of water right here. So and then it also added by the pressure by this liquid of the height of 3 meters. So and then we need to add the pressure of point number 2, which acts on this surface. So means that we could write an equation like this one. So we have the rho g of 2 meters. So and then we have rho g of 3 meters. So and then we add with the pressure at point number 2. And then because we know that the pressure at point number 2 is equal to 103.2 equal to 60 kilopascal here. So the total pressure at point B is 103.2 kilopascal. So and then we need to calculate the pressure at point C. So here please be very careful. Point C is a point at the top here. However, we cannot simply say that the pressure of point C is equal to atmospheric pressure, because this liquid, this water, is actually not connected with the atmospheric pressure, because this water has a dome here, has a layer or has a wall that separate the water here with the atmospheric pressure. So means that even though this point is at the top, it is not being pushed by the atmospheric pressure. So to calculate pressure at point C there, so we could use this idea. So we know that pressure at point 4 is equal to the pressure of point A. So and then we could calculate the pressure of point A here, as shown here, is the rho GH of this height plus the pressure that push the point at point C here. So and then we could calculate is as this one, and then it is equal of 30,570 Pascal. However, the question need to calculate the unit of pressure in terms of millimeter mercury. So what you should understand by millimeter mercury is, so previously in these notes, so I already share with you about the barometer. So we have a barometer here. So and then this barometer is actually a device that are commonly used to measure the atmospheric pressure. So the idea is very simple. So let's say we want to convert this pressure into millimeter mercury. So we have a barometer filled with the mercury, and then we assume that we have a pressure here. Okay, a pressure that act on this surface is equal to 30,570. So, and then we know that the point here is equal to point at here. So, and then this point must be equal to rho GH. So, and then we could calculate that 30,570 is equal to rho mercury, gravity, and the height of mercury. So if we calculate this equation, we found that the height of mercury is 229 millimeters. So we call the pressure at point C here as 229 millimeter mercury. Okay, please bear in mind that 229 millimeter mercury is not the pressure of this point. It is actually the height of the mercury in barometer when it is attached to this point. So you need to use this height, this distance, substitute in this equation to calculate the pressure of 229 millimeter mercury.